Right, so now let's do FRQ number 3. So here is the problem. So it has a ring, and it has it in 3 different situations: sliding only, sliding and rotating, rotating, no sliding. And it gives us the mass is m, radius is r, moment of inertia is r squared. So it wants us in part A to derive a differential equation that can be used to solve for the magnitude of the following. So A, this is part I. Okay, so part I wants a differential equation for linear velocity v of the ring as a function of time. So, and this is for the ring that is sliding and rotating. So this second situation. Alright, so what we can do is set up sigma F equals ma. Now, we know that the force that is acting in this situation is friction. So F is equal to ma, and then we know that it's mu k mg is equal to F of k is equal to ma, and here we can cancel out mass, and then we get A equals mu kg. And then we just have to remember that this is going to be negative because it is acting against. Okay, so with that, so it wants us to do linear velocity as a function of time. So we can go ahead and write that out. So we want to write dv over dt because we're deriving. And so we know that velocity over time equals a. So that means, so really we can just substitute it. So that means dv over dt equals negative mu kg. That is the answer for part I. Part II wants us to do angular velocity as a function of time. Okay, so instead of newtons, now we need to do torque. So sigma torque equals I omega. And we can go ahead and expand this a little bit more and do F perpendicular R. So what we can do is we can put in our I, which was given to us, r squared. Don't know omega, so we leave it. And then our force perpendicular, again, is going to be F of k. We already know F of k is mk, or yeah, oh my goodness. Mu mg. Sorry, brain fart. So we can go ahead and put that here. Mu k mg, and then our r is big R. And we can cancel out mass once again, and we are left with alpha being equal to mu kg over r. Okay, And again, we can kind of do the same kind of thing where we're going to have d omega d time is going to be equal to alpha. So that means d omega over d time is going to be equal to mu kg over r. And that is the answer for part II. On to part B. So, derive an expression for the magnitude of the following as the ring is sliding and rotating. So again, we're in the second situation. The velocity of the ring as a function of time for part I. So let's go ahead and set up what we know. We can use this. Our dv over dt equals negative mu kg. Okay, so from here, what we want to do is integrate time. So it's going to be t0 and then kg and then dt, and then this right here is going to be equal to integral okay, so from this you get and then you can move it around to solve for VF. So VF and that is part BI. Again, kind of the same thing, but now we're doing it with angular velocity as a function of time. So again, kind of the same setup. We're going to use this. And again, we want to integrate time because it's a function of time. And now that is equal to I didn't really explain this last time, but we want these ones, because, so D kind of is like change, delta almost. So, when you have, delta V, it's equal to VF minus VI. So that's kind of what this is showing. The problem wants us to derive an expression for finding velocity. And to find velocity, we're going to be finding VF. So we also need to include VI. So you kind of set this up so you can get that whole VF minus VI. So that's why we're using it for omega as well, because, we're using it for omega as well because, again, so that way you can have it set up because you want to find omega F, but you need to have omega initial. Sorry I didn't explain that earlier, but that is why we're using it, because you want to find these things, and in order to do that you need to account for it, initial and final. So we can go ahead and simplify this. Excuse me. Okay, and now to simplify this some more, I'm going to solve for omega final. Oops. Okay. Now this is going to be 0 because it is sliding also. So that means it kind of starts, you don't really have much of an omega initial because it is also sliding. Okay, so that is our answer for part BII. Now, on to part C. Derive an expression for the time it takes the ring to travel the distance L. So again, we're in this second situation. So what we want to set up, is this right here, because it gives us time. And then we can use some substitutions, and we have to remember that V equals R omega. So if we want VF would equal R omega F. So we can go ahead and plug in this for VF right here. And then with that, we can actually use this for omega F. So we can go ahead and plug that in. Okay, so R cancel out. So then we're left with alright, and then from here you can move things around. So then you would add this to this side. And then you want to go ahead and solve for time. And that's what you get for time. Okay, so piece of paper, on to part D. Alright, part D. Derive an expression for the magnitude of the velocity of the ring immediately after it has traveled the distance L. Alright, so Okay, so we can go ahead and use this formula again. And now that we have found time, we can actually plug it in here. You can cancel out that. Remember, 2 is still there. Simplify it. So what you have here, you have to think of it as 1 minus 1/2. So then you would get VF equals 1/2 VI, because 1 minus 1/2 would equal 1/2. And so that's kind of how this is laid out. So then you can get VF equals 1/2, and that is your answer for D. Now on to the final part, part E. Derive an expression for distance L. Okay, so what we can do is common form. So we can go ahead and set up common form. VF squared minus VI squared equals 2A, but we're going to use L instead of delta X. So we can start plugging in what we know. So we know VF is 1/2 VI squared minus VI squared is equal to 2. And if you remember from part 1, or part AI, A is negative mu K G. Oh. And then from here, you kind of just do some math. You get 1/4 VI minus VI squared, excuse me, because the squared gets distributed there to the half and to the VI. So then you get 1/4 and VI squared minus VI squared equals 2GL. Okay, so for this part right here, we have to think of it as 1/4 minus 1. So then you get negative 3/4. So it's kind of like that again, but now it's 1/4 minus 1. So you get negative 3/4 VI is equal to negative 2 mu K G L. And so we want to find L, so we can go ahead and just divide. So then when you divide, you are going to, hold on. The 2 is going to be going to the 4. So the 4 would be multiplied by 2. So when you divide it, you're going to end up getting 3 VI squared, can't forget the squared, over, and remember it was 2 times 4, so 8 UKG, and now it's not negative because a negative divided by a negative is positive, and that is equal to L. So really, just some algebra after plugging in what we know. And that concludes FRQ 3.